Hi, my name is Brad Garner. I'm a hydrologist with the United States Geological Survey in the Arizona Water Science Center. And it is my pleasure today to get to talk to you about water. But thinking about who you are and what you might be thinking about today, it occurs to me you may not know a lot about hydrology, and that's fine. You may not know some of the words that I use in my everyday practice, like riparian evapotranspiration. So I take it as a challenge to try to reach you without using words quite as big as that. I ask only for your patience, especially if you do know something about hydrology. Some of this may seem familiar to you. But if you don't know hydrology, I ask only for your undivided attention. Maybe limit the number of pop-ups and tabs that you have open right now if you're watching me on a computer. So let's begin. Imagine that you're standing on the banks of the Verde River in central Arizona. But that it's not today, that it is last June, late June 2012, a dry, hot summer day. It has not rained in 2 months, and there is no snowmelt left anywhere in the high country of northern Arizona. So no rain and no snowmelt, and yet this river is flowing. It's flowing at about 32 cubic feet per second, 14,000 gallons a minute. Now I ask you, how can this be? Sure, we've all seen rivers flowing under these conditions, but where is this water coming from? Where do you think? If you thought or said the ground, that's a very good answer. This water in this picture here is coming from the ground, and we call this kind of water, when there's no rain or snowmelt to obviously explain its existence, we call this base flow. Base flow comes from the ground, and humans can change it. Humans can change it. What do I mean by that? Am I talking about putting a pipe into the river and pumping water out? Surely we can agree that if you pump water out of a river, base flow out of a river, there will be that much less water available downstream. Common sense. Now I'm talking about something a little more obscure, less widely known, but nevertheless just as true. It's the ability for human beings, us, to pump groundwater from wells and change base flow in a river. Now, I realize that this is not necessarily the most intuitive thing. Groundwater is out of sight. It's in the ground. It's not in our obvious view. And I can understand how you might not understand this. There was a time in my life when I didn't understand it, and I'd like to tell you how I came to learn about how humans can change base flow. You see, when I was growing up, my family had this fishing cabin in central Texas. We called it the River House because not 200 feet from the front doorsteps there was this perennial stream, this river that flowed year-round. And of all the many things a young boy could love about a place like this, my favorite thing about it was this well in the backyard. We had this manually hand-cranked well, and I really loved this thing. But of course I was young. I didn't have any idea how groundwater worked, or really in a deep sense where this water was coming from. I just knew it was clear and cold, and it was our water supply when we were there. It wasn't until some years later that I came to find some basic facts about this well, some scientific data about this well. I found out that this well was 60 feet deep, but that it was only 30 feet down to water in the well. That is to say, lower measuring tape into the water and into the well until the very tip of the tape just touches the surface of the water, you would measure 30 feet. I also found out that it was 35 feet down from the very top of the well casing down to the surface of the river, measured vertically, just straight up and down. 35 and 30 are similar numbers. They're not identical. Interesting, but these were just numbers to me at the time. They had no meaning. They were just facts. It wasn't until a little bit sometime after that that I found out a bit more about how groundwater works. I came to learn that the ground is made up of rock and soil and sediments, and between all the spaces in the ground there is open space, cracks in limestones and granites, and individual sand grains that rest against one another, and there are open spaces between them, pores, if you will. And beneath an area that we call the water table, seen here as the beginning of the large blue area, everything beneath the water table, all those open spaces in the ground are filled with water. everywhere. And also this is a very common misconception about groundwater. I know because I had it once. You may share this, and let's dispel it from our minds right here and now. It's this: groundwater moves. Groundwater is not a static phenomenon in the ground. It's not like a pool that just sits there waiting to be pumped, doing nothing else. With exceptions so rare that they don't even merit mentioning today, groundwater, every molecule in the ground is moving from one place to another. Now, in the case of my river house here, it was moving toward the stream, toward the perennial river down below, to discharge as base flow. Base flow comes from the ground. And you could see this, just like you can in the Verde Valley and in the Verde River. You could see, walking along the banks, this water coming out, discharging as springs, flowing a short distance into the river. And you could also, I remember wading out on a hot summer's day into the tepid waters and feeling this cool inrush of water at your feet. This was groundwater coming in. This was base flow coming in. And so then I thought, what of this water that I would pump? You know, what of the old porcelain pail that we had, the gallon pail that we use for our water supply? Say I pump a gallon of water out and I hold it here before me, and I look at it and I ponder it. Moments ago, every drop of water, every molecule in here was in the ground, and it was moving toward the river to become base flow at some point. Don't know when. Groundwater moves very slowly, but it is not in the ground anymore. It is now in my pail. It is not moving toward the river. It is here. I have changed the system. It therefore follows, as must day the night. It has to be this way. There's just no other alternative, that at some point in the future, some point, there will be exactly 1 gallon less of water that has moved through that river system. I'm a human, and I have changed the system. And what I did was independent of everything else that was going on. It may rain more, it may rain less, but the fact that I chose to pump the well on that day has nothing to do with how much it rained or didn't rain. I have taken 1 gallon out of groundwater, and if moving groundwater is taken out, it won't get to where it was going. That's a pithy little thing to say, but it's surprisingly true. And as it turns out, this pithy little saying is one side of a coin of a concept we call stream flow capture by groundwater pumping. It's one side of the coin. We'll talk about the other side in a little bit. But now, about the Verde Valley. Everything we just talked about there was the subject principally of our investigation, the U.S. Geological Survey, in cooperation with the Verde River Basin Partnership in the town of Clarkdale. We wanted to know about how humans have changed base flow in the Verde River in the past, in the present, and what might yet happen in the future. How do you answer a question so big as that? How have humans changed a hydrologic system, a huge area of north central and northern Arizona? Well, I'll tell you what we did. We modeled. Not that kind of modeling, although I'm sure that's great too. No, this kind of modeling. Now, you may have heard scientists or engineers tell you, we built a model before, and maybe you didn't know what they meant by that. Consider this. When General Motors builds next year's great sport utility vehicle, very often they will sculpt a clay model of that car so that they can place it into a laboratory, a wind tunnel, and conduct experiments on it. How aerodynamic is it? What will the gas mileage be? Are there any strange noises that might be generated from the wind? Does this clay car have an engine in it? Does it have an AM/FM cassette stereo, leather interior seating? No. No, of course not. It doesn't need those things. It's not a car. It's a model of a car. A model represents only those essential features that are necessary so as to conduct experiments to achieve a greater understanding of the thing that is under investigation. It is a simplification of a car. We did this too, we hydrologists, but we have a bit of a harder time. Our subject of investigation is considerably larger than a car. It is the groundwater and hydrologic systems of north central and northern Arizona. It will not fit into any laboratory. And so we must model it to understand it. How did we do this? I can find no better encapsulation of what we did, I think, than the late, great Dr. Richard Feynman, one of the great science popularizers, theoretical physicists of the 20th century. He said, "This is the key of modern science and is the beginning of the true understanding of nature." This idea that to look at the thing, to record the details, and to hope that in the information thus obtained may lie a clue to one or another of a possible theoretical interpretations. It's only through such hard work that we can find out anything. And so for the last century, even more than that, the U.S. Geological Survey and other data collection agencies have recorded the details of water in north central and northern Arizona. Water levels in wells, hundreds of measurements across a century, stream flow measurements, base flow measurements, thousands of them at dozens of stations. Precipitation, how much water is falling from the sky and reaching the ground. The character of the rocks and soil, how freely does the water move through those pore spaces in the rocks. We studied these things, we meticulously recorded the data and archived it. And then, recently, we stood back, squinted our eyes, looked at everything, and said, you know, we think we have enough data here to form a theoretical interpretation, a model. We built a model. Ours was not sculpted out of clay, it was sculpted out of ones and zeros, bits and bytes in a digital computer, but it serves the same purpose. It represents essential features of the hydrology, the groundwater and the surface water here in northern Arizona, so that we can conduct experiments on it. We call it the Northern Arizona Regional Groundwater Flow Model, or I may slip and call it NARGFM, its cute little acronym. We can take this thing, having constructed it using well-understood, non-up-for-debate principles of physics, how water flows in the ground, well-settled natural law, and we see that it explains the values that we see in the data and the patterns we see in the data. Thus constructed, we can take it, so to speak, into the laboratory, and we can conduct experiments on it. Of course, we are good scientists, we are diligent scientists, we always wear our safety goggles. And so this is what we did. And believe it or not, at this point, I've told you not only essentially what we did and how we did it, but also what we found. We built a model, and we found that humans have changed base flow in the Verde River, here in the Verde Valley of central Arizona. But now to some numbers. It's going to get a little technical now. I'm a scientist. I love to actually give you numbers. You've seen none yet. One quick passing idea, though. You may not be familiar with one of our tools we use very often. It's called a time series graph. You can imagine recording temperature on your back patio once a day, and you can table these data, just have a table of them, date, temperature, but you also can graph them with time moving along the horizontal or x-axis and the thing you measured moving along the y-axis. Each point can be a dot. You can connect the dots, dissolve the points, and you're left with the essential linear, sort of the essential line that represents what the data did. We use these graphs because they can visualize a lot of data real quickly. 15 pages, 5 years worth of temperature data here, just for example, all shown conveniently in one graph where you can immediately see the rise and fall of the seasons. You're about to see some time series graphs. To the numbers then. We first look into the past. We looked from 1910 to 2005. 2005 being basically more or less the present. There's some practical reasons we didn't run right up till now in 2013. And our subject of investigation, again, was the Verde Valley, seen here. We defined the Verde Valley to include Sedona, Clarkdale, Cottonwood, Camp Verde, Rimrock, Cornville, etc. There are definitions that vary. This was our definition. And most notably, moving through the Verde Valley, to my mind notably, is the Verde River, moving from the middle left to the bottom middle here, as you see the red flow direction arrow. It enters the Verde Valley at the area denoted by this red triangle. It is where the water enters the Verde Valley. It's already a perennial year-round stream at that point. It flows through the Verde Valley, picks up additional base flow and flow from Oak Creek, Beaver Creek, West Clear Creek, and then it exits the Verde Valley at the lower triangle, the pour point, if you will, for all of the water and sort of the accumulation of all the effects that can happen to the water, the base flow in the river. You might observe them at this point. We ask the model a series of questions. We conduct experiments. And the first one is a simple question. Model, we find you apt to the task at hand. Would you please tell us what, at the upstream gauge, we call this the Clarkdale gauge, the entrance to the Verde Valley, what was the base flow in the Verde River between 1910 and 2005 as you simulate it, model? It produces the data, we graph the data, and we see something like this. Time moving along the x-axis, and on the y vertical axis, base flow in acre-feet per year. An interesting unit. If you're not familiar with it, we'll talk about some ways to convert it in a minute. And note that the graph doesn't start at 0, it starts at 30,000. We do that just so we can tease out and see the differences, the details. And there are differences. Base flow is not constant. It changes over time. And in this graph, it changes because of many stacked human effects. It went down in the human and natural effects, I should say. It went down in the 1950s because of a drought. It went up in the 1970s because of a wet period, a lot of precipitation. But built into this graph also are the effects of plants and the effects of people on base flow. It's a lot of things all stacked together. We wish to disentangle them. And so we ask the model a clever second question. We say, model, we find you apt. Tell us, what would base flow have been at the Clarkdale gauge if there never had been any human stresses in north central and northern Arizona? No groundwater wells, no septic tanks, anything of that kind. No stresses on the groundwater system. We produce this line. It is higher. There is more water than the line below it. And for mathematical convenience, we can subtract these two lines. A little easier thing to look at. You subtract the two, produce one line, and this is what we call the relative change in base flow attributable to human stresses, namely groundwater pumping. And we see that in 1910 there were no human stresses on the groundwater system to speak of. The change was 0. But then as we move forward through time, starting somewhere around 1940 or so, base flow begins to decrease. And by the year 2005, we can measure the difference between 0 and the final resting place of that line and see that it is a decrease of about 4,900 acre-feet per year of base flow at the Clarkdale gauge, at the upstream end of the Verde Valley, and this is attributable solely to human stresses, namely groundwater pumping. We have subtracted out all other things that can change base flow, leaving only this. We move then to the downstream gauge, the Camp Verde gauge we call it. It's downstream of Camp Verde, past Beasley Flat, near the Verde Falls, the pour point, again, of the Verde Valley. And we ask the same question, do the same graphs, same math, and we produce this line. It is similar in character, but different in shape and magnitude from the upstream one. Here we see, moving from left to right, it begins at 0, but by 2005 there has been a decrease at the downstream end of the Verde Valley of about 10,000 acre-feet per year, attributable to human stresses, groundwater pumping namely. If you're not familiar with 10,000 acre-feet per year, here's some handy, quick things I came up with, some clever conversions. If you're a kayaker, you may be familiar with cubic feet per second. Other people besides kayakers too, but 10,000 acre-feet per year is about 14 cubic feet per second flowing at a constant rate all year long. It's also about 6,200 gallons per minute, or cleverly, about 2,500 shower heads running at full blast. It's about a 2.5 gallon per minute shower head. This is an interesting one. It's about an Olympic-sized swimming pool every 2 hours, actually a little less than every 2 hours. And also, it is 12% of the base flow that we measured at the Camp Verde downstream gauge in the year 2005, or that the model said was base flow there in 2005. So it is 12% roughly. Not 50%, not 90%, not 100%, about 12%. Humans have changed base flow. And so this was our retrospective look into the past. We then turned our eyes to the future. The hypothetical future. Why would I put the word hypothetical in front of the word future? Isn't that redundant? Well, maybe it is. Some people say it is, but here's what I was thinking. When people talk about the future, very often I think they're sort of thinking about a crystal ball, perfect knowledge of the future. And I think most people would agree that where humans are concerned, the future is somewhat unknown. We are not just chemical reactions proceeding deterministically. We have intelligence. We make decisions. So what will north central and northern Arizona look like at the dawn of the 22nd century? Well, number of people, how much water will they need? There are ways to address answering that question, but the USGS, we said we have no crystal ball, not that I know of, no one's told me of it, so we said we don't know exactly what the conditions will be, but we don't let that stop us. We can still conduct experiments to see what the connection is between human stresses and base flow in the river. And we did it this way. We said, let us take groundwater pumping as it existed throughout north central and northern Arizona. Now here, for convenience, I'm just showing you the pumping rates in the Verde Valley, but we did this technique all across northern Arizona. Let us do three things. Number one, take the values, the pumping that existed in 2005, and hold them constant out to the year 2110. Condition two, an increase of about 3% per decade for 5 decades, and then constant for the remaining 5 decades. And condition three, which is just the mirror image of the previous, a decrease of 3% per decade. We pose these three experiments to the Northern Arizona Regional Groundwater Flow Model, and we look first at the upstream Clarkdale gauge, and we look at the output. We graph it, and we see this. Not one line this time, but three different colors representing the 3 different experiments. They start at 0 on the left, and as they move to the right, they begin to decrease, and they separate from one another. They're rather tight together, though. This indicates that depending on the amount of hypothetical future human stresses, there will be an additional decrease in base flow of about 2,700 to 3,800 acre-feet per year attributable to groundwater pumping, human stresses, at the upper end of the Verde Valley 100 years from now under these hypothetical conditions. We do the same thing, briefly, down at the downstream end of the Verde Valley, the Camp Verde gauge, and find, again, similar in character, different in magnitude, kind of that fireworks spreading out pattern, an additional decrease of 5,400 to 8,600 acre-feet per year attributable to pumping. Additional is kind of a key word here. Remember that at the left of this graph, in the year 2005, there already has been 10,000 acre-feet per year decrease attributable to pumping. So these changes, these negative values, are in addition to that which has already taken place. There's a lot of numbers for a short period of time we have together today, so let's kind of review where we've been. Take a step back, look at the bird's eye view. We've talked about the movement of groundwater, how it moves from one place to another. And in north central and northern Arizona, it is moving toward our perennial streams. Not just the Verde River and Oak Creek and so on, but also Fossil Creek and Sycamore Creek, the Little Colorado River, the Colorado River. This is where our groundwater is moving. And talking about my childhood fishing cabin, the river house, we observed that if you take groundwater out, it won't get to where it was going. In this diagram, you can see it is intercepting water that otherwise would have reached the river as base flow. This is one side, we said, of stream flow capture by groundwater pumping. The other side of that coin is this kind of diagram. It is also possible for a groundwater well to pump and actually draw water in from a stream into the aquifer. Now this can happen anywhere, and the direction of groundwater flow can actually change over time. You can have, at one point in time, what's called a gaining stream, like the Verde River in the Verde Valley. But in the future, if groundwater pumping and conditions change, it can turn into what we call a losing stream. Now all of these things, what of this? What are we about here? What is this all about? Well, it's science, isn't it? Ask 10 people, what does science mean? And I find you'll get 10 different answers. At least 3 of them is, I have no idea, which is fine. There are a lot of working definitions for science. There are a lot of different ways, different methods of science to employ. But at its core, in fact, literally at its core, it's etymology. If you looked it up in a dictionary, the word science means knowledge. And I like to think of knowledge, everything, the sum total of what we know as human beings here on Earth, as this huge edifice that we are building, this enormous brick wall. And we build it brick by brick, layer by layer. And the upper layers cannot be built until the ones underneath them are already there to support them. And science is a tool, a technique for placing these bricks in place. And this Northern Arizona regional groundwater flow model is a brick in the edifice of knowledge that we are building. Now, the scientific investigations that we have talked about here today are additional bricks built on top of that model. They use the model to answer experimental questions. We find it apt to the purpose, and we use it for this. We also find that the model is our best known summation of the knowledge of the groundwater systems of Northern Arizona. And these models and these reports, these experiments can be used by water resources managers. Those are the people who are in your community who make decisions about how water gets used, how much people are charged for it, and so on. Elected officials find it relevant. You, the voting public, might find it relevant as well. But to be clear, there is a strong red line, if you will, on this diagram between these two. And the USGS, we stay in the upper half of this diagram. We conduct the scientific experiments. We're not a regulatory agency. We don't tell people where to pump, how much to pump. Those are the tough decisions that resource managers make. We provide the information. And we like to say that what we provide is policy neutral, yet policy relevant. Have we been revolutionary here? Have we done something never done before, truly? Well, I'd like to think so. I was the principal investigator on this scientific study. I'd like to think that this quantification, this putting numbers to how humans have changed base flow in the Verde River in the Verde Valley is something new. But in other ways, this is not revolutionary. People use groundwater flow models all across the country, all across the state. Phoenix has one used for resource management. Tucson, and even Prescott has a Prescott Active Management Area. These are models that are used for applied decision making. Even more fundamentally than that, really, we're just, in a specific way, we're restating what was said over 70 years ago by C.V. Tice. He wrote, "All water discharged by wells is balanced by a loss of water somewhere." This is well understood, well settled science, not up for any serious debate in the hydrologic science community. Today we put it a little more colloquially. We said if moving groundwater is taken out, it won't get to where it was going. But above all, I would ask you, as this presentation ends today and you wonder, what have I learned, what have I taken away from this, you might consider that base flow comes from the ground, and humans can change it. I thank you for your time and attention today. I'd like to thank my co-authors, D.R. Poole. He actually was the crafter, the sculptor, if you will, of the groundwater flow model we used. Fred Tillman, Brandon Forbes, and also a thank you to Jim Leanhoutz, Dave Anning, my colleague and good friend, Bruce Gungle, Kim Beisner, and of course my parents, Steve and Ann Garner, who had that wise foresight to buy the fishing cabin.